Lorentz, being a well-educated mathematician, made few inventions looking at this project, his own little project. And one thing he knew is that when you have a flow and it looks wiggly and complicated, a Poincare section might be helpful in organizing it. Here is one interesting topological, fundamental property about the world of Lorentz. There's an invariant subspace. Remember, there was a symmetry of these equations. If I rotated x and y by 180 degrees, then x would become minus x, y would become minus x. But z was the axis of rotation, so nothing changed, which means that there is an invariant subspace. If you write the equations of motion on this invariant subspace, you will discover that if x and y are 0, you're on z-axis, then equation becomes very simple. Z dot becomes minus parameter b, one of the parameters that is in the original equation. Well, called, b. So if x and y are 0, this goes away. So I have one-dimensional motion. If x is 0, it doesn't couple to y, doesn't couple to x. So world on the x-axis doesn't cause any change in xy coordinates. It's an invariant subspace. It has a property that this coordinate is invariant under the symmetry of the problem. Now, whenever there's a symmetry, you want to look at things that are invariant under it, and it turns out z is a natural coordinate to do that. What Lorentz did is he looked again at this sequence in time that's jumping, but he did it for z-axis. Now, what happens to the z-axis, if you look at this in this three-dimensional projection, the orbit goes up and down, but it never goes down to the origin because it's quite unstable. But it has its maximum, minimum every time you go around. So, and it's positive. So it looks something like that. Get close, oscillate, get smaller, jump again. And this means, you get close. So you see a signature before every jump, you get very far away from the center and then this thing happens. So, it seems to be nicely related to jumps. And he said, well, let me look at these points where I was coming down and go up. So the extreme of this curve. So this is z coordinate. And this tells me, how close I came to this plane before I jumped. So it's a set of points. In the real equation, in a real space, you can estimate the time running around here. It's given by the complex eigenvalue of the center. So you have some sense of this time scale. But getting to the lowest point is not a multiple of it because it's a nonlinear problem. It's not a bad guess. So this is fast frequency. So let's call these guys, let's say Z0, C1, Z2 for this one, and so on, Z28, whatever. So every time I encounter a minimum, this actually is a Poincare section, not of the flow, but its derivative, because every time derivative of the flow is 0, you say blimp, and that's how we defined Poincare section before. So now you can study what happens in that Poincare section. It's a three-dimensional flow. So Poincare section should be two-dimensional because it's one-dimensional less, but you ignore that fact. And you just start plotting what z is, successive values of z's, and you get something like this. If you start here, you find next one is here, next one. That means you're running around and you're counting minima before you jump. And then you jump and you record it, and then you jump, you record it, you keep doing this. So the trajectory here is jumping all over the place. And what you see is, it looks like it sits on a one-dimensional line. So he says, well, suppose there was a Poincaré map, which is actually one-dimensional. That's this function you see here, Poincaré section. It was defined by saying there is a function, Z, define the lowest points where my trajectory, sorry, at time Tn, divided function time experiences a minimum. That defines the nth value of Z. Then you have a Poincaré map. Every time you satisfy this condition, you mark it. And it looks like there is a function, just looking at your numerical picture, this function that fits. Now we're in the world of numerics, so you compute it numerically, you use your cubic splines or whatever you like to write that function and call it Poincaré function. And now you notice the following thing. This Poincaré function, its slope is always larger than 0. Just look at it. It cannot be less than 0. So you observe as a fact that your numerical Poincaré return map, its slope is always larger than 1. If it wasn't, you'll be on diagonal. This is slope 1, but you're always above it. And you learn that there is no stable periodic orbit, because any periodic orbit has to be on this function. It has to jump between the branches of it. But the local slope is larger than 1, so multiplier has to be larger than 1. We already know that there is no stable equilibrium. That was elementary. And we already know that average divergence of the flow is smaller than 0. So that's one attempt to define strange attractor. The strange attractors are really very hard to define, but this is the intuitive notion. I seem to be confined to something whose section is one dimension. So I seem to be confined to 2 dimensions. It'll turn out it'll be a little bit more than 2 dimensions. It'll be a fractal dimension, but here it looks like it. And it looks like you are running around it. Everybody is unstable, so there is no possibility of finding. So there is, for example, fixed point here, and there is our equilibrium that we know here. So there is a periodic orbit, which when I look back what it means, it'll turn out it'll be some kind of figure 8 that runs once this side, jumps, runs once the shape of this orbit in a full space. But its slope is larger than 1, so it's unstable. You are living in a world where there is no peace and there is no rest. And in this particular case, Lorentz was so lucky that when you do it really rigorously as a mathematician and you don't cheat, I'll explain why we are cheating. Let me explain it. It's important to understand why this is enough to make you famous to prove this. So we do not have an analytic expression for Z. We can try to fit it by splines, polynomials or something. It's some function like that. So we can try to find a smooth function like that by fitting and say that's what it is. I computed it by numerical investigation. But it's hokey because Poincaré section is 2-dimensional. 3-dimensional, it's plane. So how come one coordinate is enough to describe it? It's a cheat. It's not honest. So if I take a magnifying glass and I magnify this by factor 10 to the minus 4. So I take a little area here and I look at it closely. So one of my friends did it to incredible precision. So I blow this up. So now in a blow up of this little region, I look carefully what these points are doing. And what I discover is they actually sit on little lines. There is no one line. There's a bunch of them. And the more I use my magnifying lens, I get more and more lines where I sit on, smooth lines, but separate lines. And that means this is not a function, because it means that if I, function has unique value. So if I look at a particular value of x, this can take, turns out, an infinite set of values. So that's why pretending this is one-dimensional is a cheat. They kick you out of math department if you do this, and they should. It's dishonest. To pretend it's simple in a very profound way, it's not. And we'll discuss this a lot. It's not a function. Lorentz was a working person and I'm a working person. It turns out that if you put, your blinders on or you're slightly myopic, it is very good to call it a function. And to understand this, we will actually now move to the world of maps. See, this is a one-dimensional map, meaning the next state of the system is a one-dimensional function or a map of the present state. So we are explaining the system by saying, if I knew where I was on this one-dimensional line, a good course on chaos in math department, for example, one by York, Oligood, and Good undergraduate course, ignores differential equations totally. Everything we've done so far, it's way too complicated for a mathematician. It starts with maps, and if you don't care what things mean physically, you're perfectly happy. But now we have a very strong motivation, starting with our systems with the continuous times in flow, then using Poincaré sections as convenient devices, numerical devices, to organize various parts of the flow. And realizing that in interesting situations like weather, these things actually have a life of their own. They are maps that were derived from differential equations, but they have lots of wonderful properties themselves. So that's our next task. We are doing outrageous things now. I mean, this is a big jump. First, we went to 3 dimensions and we lost predictability. The weather became unpredictable. And now I'm going to inflict upon you a piece of mathematics that you would naturally never, as a serious physicist or chemist or biologist, never consider. Ibrahim, it is called topological entropy. So, but it's a little bit subtle, and there's something called metric entropy and Kolmogorov entropy, because you have to decide whether you count how many ways you come back. That's a topological notion. You just count different ways of going to the left room, right room, basement, coming back into the room where we are. That's what could happen to a teenager trying to run away. Or are some of them more important than other, whether you have to put the weights on it? And that's why it's not as easy as it sounds. It's topological entropy, or Kolmogorov entropy is the, deeply correct way of counting numbers of ways, which is weighted by a likelihood that certain paths happens. And that's too hard to define now.
If someone has a function of n and then he plots z, n plus 1 versus gn, you mentioned that this is cheating and this is not a curve or this cannot be a graph because if you get a magnifying glass.
Excellent question, man. So there is here, first you have to understand how this is constructed. So when your trajectory in continuous time and space runs around, there's just one continuous line. And when it's close to one of these equilibriums and your Poincare section is someplace, let's say this way. Suppose this is your Poincare section.
Okay.
Then you count this point, this point, this point, and they come in sequence. So that makes sense. But when you come here, it jumps over to the other side, and it can land any place, and it can do this and jump over to the other side. So this trajectory in full space is jumping between left and right part of the strange attractor, which means that its section, it cuts, jumps between this and that branch of the system. So the way, it's a very nice thing to do to yourself program it and run it. So it just fills it up in a very irregular way. You get dots, 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 dots. You wait for 1,000 or 10,000 dots, and it looks like a smooth curve. Now, it looks like a smooth curve because your printer or your screen is using resolution of 1%, let's say. But the distance between these guys is at least 10 to the minus 4. Now, how we know it's 10 to the minus 4? We know the strength of contraction in the stable neighborhood. And we know that every time we go around, we get closer to this plane by factor 10 to the 4. So we can estimate this number. As I run around, I'm being compressed toward the plane or curve on which this curve is. And every time I get closer, and that's what produces these layers. You will see this will be layers of kneading a Danish paste. It's totally non-obvious, a set of points which, just come up on your screen, lie on curves. So there is no obvious way in which you could write an equation for these curves without thinking. If you think, they have to do with unstable manifolds, so there is a thinking. It's not obvious how you get this. As far as I know, except in trivial cases, it's always numerical. Nobody can produce an analytic formula for this guy from the original three-dimensional Lorentz equation. Never happens that I'm aware of. So it looks like a function. It's not function, but if you work in person, it is pretty good function. The fit is really helping you. Now, I can give you one example where the fit really helps. One way of doing celestial mechanics, so trying to understand how all the planets in the solar system move, is to construct a Poincare section in the space of all planets. Each one of them has 3 velocities, and it has 3 coordinates to say where it's in some absolute celestial frame. So, there are lots of dimensions, 6 times 9 or whatever you're including. So in a large phase space, but you can construct a Poincare section, which is 1 dimension less. And instead of running all these differential equations for everybody running a different velocity, etc., you can actually construct numerically this map. Now, it's a 10-dimensional map or 26-dimensional map, but a very clever professor at MIT can do that as a life work. And then what happens is, instead of measuring the age of our solar system in seconds or minutes or whatever you're integrating your equations in, you measure it in this finite time of the whole system returning. And that turns out to be a big jump. So it turns out you can speed up evolution of solar system by factor, let's say 1,000 to 1,000,000 if you do this cleverly. And you can suddenly evolve it in millions of years rather than in seconds and minutes. So that's an amazing application of this idea, because getting from the flow to the map is not a simple thing. But this justifies now going off over to the world of maps.
It seems to me
that know everything. What do you say?
It seems to me that the Poincare sections are not super unique or well defined for
No,
just like general.
it's a very good remark. Thanks a lot. It's a totally dark art because, you enter this room and it can be very high dimensional, not just 3-dimensional. And there is something buzzing all over the place on a continuous trajectory following its law. And then you go around and you try to see, can I put some surface in the space, 1 dimension less than the flow, in such a way that I cut as much as possible of this flow. And there's some rules of thumb. If you have equilibrium, it's convenient to send the surface through the equilibrium, so everybody who comes close to the equilibrium is guaranteed to catch a Poincare section. But it is totally a dark art. It's artistry to find good Poincare sections. And every artist, maybe in Japan or someplace that finds one, produces a picture that's different from anybody else's picture, because when you cut flow in different places, you get different looking sections. So, and we don't have, we can help you. In the Chaos book, I suggest how to choose Poincare maps. But basically, if I'm moving on planet Earth, I have the idea of cartography that I make local charts, put them together, and, I get nonlinear coverage of our spherical planet. But general nonlinear system has very complicated geometry. It's nothing as simple as a sphere. And we are usually at loss of how to organize parts of it. It's one organization by these Poincare sections, but it's really, really requires lots of experience. This particular problem, not any problem. So, trying to understand the Poincare, a chemist called Rosler, classically educated, fluent in classical Greek and Latin and God knows what other languages of antiquity, but working in 1980s and 1990s. Now in Germany, this still exists because they have classical gymnasium where people learn these things. Rosler said, well, this is nice, but it has these two stupid mirror images of each other because it has discrete symmetry. So let me think of a simpler system. And he thought of something simpler, which, there are pictures in Strogatz and lots of pictures in Chaos book. So we're still in 3 dimensions. We still have this equation here. I mean, this equilibrium, it's actually not exactly the origin, but close to the origin. We still have unstable guy here. But only one, not a copy. So don't use mirrors to complicate your life, make it very simple. Turns out it has a motion that if you start close to this, you run around like this until you hit, in this case, you hit this unstable manifold. In his case, you hit some strongly expanding direction off the plane. You hit it, and you go off, and you fall back. And you run around, and you go off, and you fall back. You run around. And the reason why that system is very nice, and I recommend using it. It's simply the Lorentz system. It's equally useless as description of weather or chemistry or anything. It's only here for you to develop intuition. But if you look now at Poincaré section, which is some radial direction Rn and next Rn, you end up at the thing that looks like that, which is colloquially called a parabola, but it doesn't have to be parabola. It just have to have one part close to equilibrium in which you grow. It has to have a critical point where this whole thing folds. So you get an edge, and then everybody who is a little bit further out ends up closer after folding, and that's what this branch is. I'll explain that in more detail next time. And this is called a unimodal. You know, uni because there is one place where it gets folded. Modal because God knows what, but that's what mathematicians like to call it, unimodal map. And what we will now do, it's easier to work with than this guy because this guy turns out to be singular. It has to do with this invariant subspace C. So we could have used original Poincaré map, but this one we can just write as an equation, which already we did because we have written something that looked like Verhulst equation when it was differential equation. So, you know, parabola had 0 here and 0 at 1. This is 1, 0, 0, 1. But now we say this is the function at time n. It counts back at time n plus 1. And it turns out this is a pretty good description, qualitative and sometimes quantitative description of differential equation where you have instability, oscillatory instability in plane, and then nonlinearity, you know, shooting you up, folding you, and sending you back. So there are lots of good examples in fluid dynamics, chemistry, biology, etc., where this kind of function happens. But for purpose of the course for a while, this is the first time you have a map, which this would be a linear map if there was, sorry, I've forgotten an important thing. There is one parameter for this map called A. This would be the slope close to the origin, but it's nonlinear because it has a second term. And we can learn a great deal about what it means to work in nonlinear world by understanding this x squared. This is first nonlinearity. Happens always. You know, it becomes a very cute mathematical game. So whenever you say, well, why am I wasting my time on cute mathematical games? Just step one back and say, I'm solving a real problem in weather, and I've used a clever trick to reduce it to a map. And if I don't understand maps, I understand nothing about weather. So that's why I'll do it.